Hello, my name is Dominic Wadagno. Unfortunately, the second Friday of semester, I did not have a project proposal ready. So here it is. I'm interested in transformers and machine learning. So I have made nets in the past. I have made long short-term memory, or LSTM, networks on stock data. I just use stock data because it's readily available. The way I made my LSTMs is here. I literally just got the data, took some statistics, and plugged them in. So an LSTM uses 4 gates. You have the forget gate, the input gate, candidate values, the output, and the hidden layer. So that's how it updates, right? And I put 3 layers. I think there's like 40 something epochs, and it should spit out, a number. It also, so the weight matrices, everything is trained through gradient descent. Yeah, but originally got me into stock data was my final project for this class, numerical calculus, where I essentially took stochastic differential equations and I plugged them in and simulated them with Monte Carlo. So I took a bunch of stock data and then I took them and I simulated 1,000 paths according to a couple different models, a couple different stochastic differential equations. Like here's Black-Scholes, and here's the Heston model, which is like a model with variable volatility. So doing that, it gave me the motivation to try and combine the two with this kind of neural net. So this is like a more Bayesian approach. You have your weights, your weight vectors are not normally distributed random variables with the standard deviation, the mean here. So that's pretty much the main difference between that and the other one. It also has the confidence bounds, which I didn't mention, are also here. That's why they're shaded. Like the pink here is that's like the 95th confidence bound. I don't remember why I did 68 and 95 here, but yeah. And then these are estimated using gradient descent, where I had to use, I did a bunch of optimizations because I was getting exploding gradients everywhere. So Atom W is it's like heavy ball, but it's got a little different. What makes me want to research this? Attention. Attention is like the main mechanism behind transformers. So I wrote this little paper, which is recurrent neural network. It's literally just you have an input, multiply. So you have a weight times that input, and then it goes into your classification function here, which is whatever you want. I guess whatever you want it to be, as long as it doesn't explode. And then you get an output, and you can do what you will with that output, whatever. So that's how it works, and I'm sure there's a million other ways to train it. I know LSTM is a type of RNN, but yeah. So it's like a very basic thing. Here's all those equations. This is literally. So this is how you would use attention for said model. I don't really understand why. Like it seems to me like attention is just a completely different way of thinking about things. Like fundamentally, instead of taking sequences of data, you take this value or values, and it kind of just works. I don't know how the parallel processing works or any of that stuff regarding these types of models. Given input, create these matrices. So I know that there's the backbone of attention. You have the queries, keys, and values, and it's defined this way for, I think, in general, transformers. So you have QV, so the queries, keys, and values. This is the dimensionality, it's square root of the dimensionality, it's the scaling thing, this is your values, and softmax is just this function here. So the input would be QK transpose over square root of DK. So, and I talk about multi-head attention, which I'm not even going to begin to understand yet. So, transformer architecture it's really just like all attention mechanisms, which I really want to learn more about, because this is kind of like a new strange thing to me.